In this chapter, we will be exploring exponential functions. In this lesson, we will be looking at the characteristics of exponential functions.
Okay, so in this case here, in this lesson, what we're going to do here is introduce the exponential function as a graph. Okay, something that you could look at on your calculator if you wanted. So we'll start with just a basic definition. An exponential function is a function whose equation is written in the form, and let's zoom in on this here. Whoops. Right here, we'll zoom in. It's a function written in the form of a times b to the x, okay, where b is greater than 0 and b is not equal to 1. Now we throw this restriction on here because if you let b become negative, okay, well first of all, as b is 0, it's just boring. Okay, it's just 0. The whole function just collapses to nothing. But if you let b go negative, then you introduce the possibility of taking the square root of negatives, and that becomes a kind of a function that we're just at this point we're not interested in working with. Okay, still interesting math, just not at this level here. So here's our general exponential function. So now let's zoom out a little bit here, and we'll take a look at just a couple of variations on this. The only stipulation that we made here, the only couple stipulations, b had to be positive and it had to be, it couldn't be equal to 1. Now again, if b is equal to 1, it's just a boring function. The whole thing just 1 squared, 1 cubed, 1 to the millionth is just going to be 1. It's just a boring function, not very interesting. Now, if b is greater than 1, okay, then the graph looks like this. What it does is it rides along the x-axis really tight, okay? And then once you get close to the y-axis here, it starts to increase, and then it increases really quickly here. And we call this a growth function. So if b is greater than 1 here, then the graph is a growth function. It gets bigger very fast. In fact, when people talk about exponential growth, that's what they're talking about. Really quick. Now, on the other hand here, if you let b be a fraction between 0 and 1, you get the same sort of motion just in the opposite direction. Now, we typically, though, read these things left to right. So now, instead of riding along the x-axis and then swooping up really quickly, this thing starts really high up at positive infinity, and then it drops down really quickly. And then once we get past the y-axis, then it starts to, it basically tries to change direction here. It's approaching the x-axis. It just levels out here. It never quite gets to the x-axis. It just gets closer and closer. But because this thing drops the way it does, we call this a decay function. Because the value is decaying. It's getting smaller and smaller as you go to the right. So two different possibilities here. We got this growth function, we got a decay function. This happens if the base of the exponential, of the power, okay, is greater than 1. And this happens if the base of that power is between 0 and 1. Some other characteristics that you should be familiar with, okay? The y-intercept is always going to be 0, a. That's essentially because if you let x go to 0 here, which is what you would do if you're looking for a y-intercept, you'd make x equal to 0. b to the 0 is 1. We saw that before. And then 1 times a is just going to be a. So the y-intercept would naturally be a. Okay? There's no x-intercept. This function here, there's no value of x that causes this to be equal to 0. Now before someone says, well, what if I put 0 up there? No. Remember what we just said here. If you plug 0 in there, okay, b to the 0 becomes 1. Okay, it's not forcing this whole thing to go to 0. So there's no x-intercept. It gets really close, and in fact, what we do here, we call this, it approaches the x-axis. Okay, it approaches the x-axis, but it never gets there. Now we call that horizontal line, the x-axis, we call that a horizontal asymptote. Okay, so this asymptote, well, not asymptotes, but asymptote. That horizontal asymptote, that line is a line that the graph approaches, never actually gets there, never becomes the line there. So for example, up here, this graph, as you go to the right, it approaches the x-axis. It never actually gets there. Okay, it just gets closer and closer and closer to it, never actually gets there. We call that a horizontal asymptote when it's a horizontal line there. The domain is all reals. You can plug in any number you want in for x, doesn't matter, it's going to work. And the range is going to be y is greater than 0. This thing, just like we said up here, it never hits the x-axis. It never actually gets to the spot where y is equal to 0. It gets really, really close. You can get as close as you can imagine to the x-axis, but you never actually get there. So these are the other characteristics of that graph that you should probably memorize. Now we're going to take a couple moments here to go on and look at some example questions that you might get.
Decide whether each of the following functions is exponential or not.
Okay, so when we're looking for exponential functions, we are looking for functions, okay, specifically where the variable, the x variable, is in the exponent, and the base isn't 1 and it's not negative. Okay, now here, this one is not. Okay, this is not exponential because the variable here is sorry, did I say base before? I'm sorry. We're looking for places where the variable is in the exponent. Okay, it can't be in the base. In this case here, it is in the base. The variable is in the base. That doesn't count. So this is not because of the fact that the x is down in the base. It should be up in the exponent. Here we go. Now the variable is up in the exponent. That's a great first step here. Look at the base. The base is positive and it's not 1. Yes, that is exponential. Oh, look at this one. Once again, the variable is not in the exponent, so no good. That is not correct. Okay, good. The variable is up in the exponent. That's great. That's a good first step. Now let's look at the base. The base is a fraction, but as long as it's not negative, and as long, okay, sorry, it's not 0 or negative, and it's not 1, we're good. That is exponential. Excellent.
Determine whether each graph represents an exponential function or not.
Okay, so we're doing the same thing as the previous question, just this time we're looking at what the graph looks like. So look at this guy right here. If I just kind of anticipate this continuing on in both directions, this is going to swoop all the way up, and this is going to drop down, but it looks like it's getting closer and closer to the x-axis. So my gut on this one is, yeah, that does look exponential. It looks like the base, okay, we're looking at an exponential here, where the base is between 0 and 1. Okay? It's going through, it's got a y-intercept here of 1, maybe the a value here is 1, and that looks exponential. This one right here, well, it's kind of just the reflection of that last one over the y-axis. Now it's starting low, starting along the x-axis, and then it swoops up really quickly here. That's what I would expect an exponential function to look like. So yeah, that looks exponential. In this case here, it looks like an example of one, a growth one, where the base would be greater than 1. Okay, now this one here fails to be exponential because look at what it's doing here. It's changing directions. Now not only that, I can clearly see that this thing has got x-intercepts. Okay, and it's dipped below the x-axis. I can see here that the range is going to be all reals. So no, this isn't an exponential. In fact, this one here would be, this is a polynomial. This is going to be like a cubic, is really what it would be. This is like some value of, sorry, it's going to be an x cubed multiplied by something, adding a square or whatever. It's going to be a polynomial, so not exponential. And for a very similar reason, this is not exponential. Okay, again, I can see it's got these x-intercepts here. I know my exponential function shouldn't. It dips into the negative part in terms of my range, and I know my exponential function won't do that either. Okay, it should be approaching the x-axis in some direction here, and it doesn't. It moves away from, no matter whether you're going left or right, it's moving away from it. So no, this isn't. And actually, truth be told, this again is a polynomial, and this is going to be like your 4th degree. Okay, what we might call a quartic, because it's got that special little pattern that we would associate with a 4th degree sort of function.
Which graph represents a decreasing exponential function?
All right, well this function right here is a straight line. Okay, this thing here is linear. Now it's decreasing, which is one of the things we're looking for in this question is that it's be decreasing, but this is simply a linear. This is a decreasing, okay, linear function. That's not what we're looking for in this question. Let's look at this one. Oh, look at this. If I was to extend this pattern to the left and to the right, to the left this thing would go up to infinity, to the right it looks like it's getting closer and closer to the x-axis. That communicates to me that this is exponential, and it's dropping as we go. So yeah, this right here, this is a decreasing exponential or a decay function. All right, so B, the second one here, that's definitely a decreasing exponential. Now let's see if anything else is here. This one right here, okay, well, first of all, it's not decreasing. This is increasing. And we always talk about increasing and decreasing as when we consider the graph and we glance from the left to the right. Like we're scanning this thing left to right. As I scan this left to right, the graph goes up and up and up. So this is increasing. And it's definitely not exponential because, look, we've got an x-intercept. We got a part of the range that's negative. That is not exponential. In fact, this is a polynomial. Okay, and more specifically, it's a special. It looks to me like a special type of cubic. Let's move on to the next one. Okay, well, this one looks more exponential. Okay, if you go to the left, it looks like it's getting closer to the x-axis, but okay, I anticipated it wouldn't hit it. If you go to the right, man, it looks like it's going to shoot up really, really quickly. So it certainly does look like it's exponential. But as you go left to right here, it looks like it's increasing. This is an increasing exponential. So again, this is not what we're looking for here. The only one that fit the descriptors that we were looking for was this one, a decreasing exponential, or a decay function.
Complete the table with reference to y equals ab to the x.
Okay, so for this question right here, we're just going to start to compare specific exponential functions to our general pattern here. So take a look at this guy right here, y equals 5 to the x. Now notice in our general expression here, we've got our exponential part of it, this is the power, b to the x, and then we're multiplying it by some constant. Okay, a is not part of the base. It's different, it's multiplied out front here. So take a look at this. What's the power here? Well, it's 5 to the x. Okay, is there a number, do you see a number multiplied by that? Well, no. And so if there's supposed to be a coefficient there, but we're not writing it, then that coefficient is assumed to be 1. This is 1 times 5 to the x. A is not 5. Okay, the base of the exponential is b. The base of this exponential is 5. So the value of b down here, this is 5. That's the exponential. Now, what's my y-intercept? Well, my y-intercept will occur where x is equal to 0. So 5 to the power of 0, that's just going to be 1. And notice that it's going to be the same as the a value. We've already seen that in a previous example. Is this going to be increasing or decreasing? Okay, is this a growth function or a decay function? Well, look at the value of b. All I need to know about this is whether it's greater than 1 or between 0 and 1. In this case, it's greater than 1, so this is going to be increasing. Okay, this is a growth function. Let's take a look at the next one. All right, well, this is a little bit more clear because it visually follows the pattern that we're looking for here. The value of a here is 2. Okay, the base of the function here, or the base of the power is 3. Okay, so that's going to be b is equal to 3. Now my y-intercept, I already know that my y-intercept is going to correspond to the a value. 3 to the 0 is going to be 1. Again, that's how I find the y-intercept to make x equal to 0. Multiplied by 2 is going to be 2. Those two are going to be the same almost all the time here. Is this increasing or decreasing? Well, that depends on the value of b, and because this is greater than 1, this is going to be increasing. Good. Look at the next one. Here's another one that I can clearly see by looking at it, the a and the b out of this. In this case here, the value of a is 5, and that we should now start seeing the pattern. That means that the y-intercept is going to be 5. The value of b, the base of the power here, is 1/2. because it's 1/2 to the x. And because this is now between 0 and 1, this is going to be a decreasing function, a decreasing exponential. And finally, in this chart here, again, 2 times 1/3 of the x. The value of a here, and I can see it clearly multiplied out front here, is going to be 2. So the y-intercept is 2. The base of the exponential is 1/3. And again, because that base is between 0 and 1, okay, I know that this function will be a decreasing function.
Match each exponential function to its graph below.
Okay, so with this matching question here, let's take a look at the graph here. First of all, the equations, y equals 5 to the x. Okay, well I know, and because I saw this specifically in the previous question here, I know that the a value is going to be 1, so we're going to have a y-intercept here of 1. I know that it's going to be a growth function, or an increasing function, because the value of b, the base of the exponential, is greater than 1. So it can't be this one, because this is decreasing. Okay, it could be this one. It could be this one. So this is a possibility. Let's look at the last one here. Okay, well it ain't this one. This is decreasing. This is decay. So by default, this has to be, okay, that first one here, this has to correspond to y equals 5 to the x. Okay, next. Next we've got y equals 1/4 to the power of x. Now this has got to be a decay function because the value of the base is less than 1. It's between 0 and 1. So it's got to be decay. But I already anticipated that because my graphs A and C were both visually decay functions, decreasing. Okay? So now what we want to do here is, let's take a look at the y-intercept here. Well, my y-intercept is going to be 1 because my a value is 1. So let's take a look here. Okay, well this is a good candidate. My y-intercept is 1. Let's take a look at C. My y-intercept is 1. Oh. Okay, so now let's take a quick look at these two together here because they're apparently very closely related. Oh, look at this. 1/4 to the x, 2/3 to the x. Okay. Okay. So we've got y equals 1. As our y-intercept, y equals 1 is our y-intercept here. The difference is the bases here. Okay, the difference are the bases. Now, what this means, okay, we have to compare the graphs here. Now, think of it this way. If you compared, what I'll do is let me pull this out here because this might make more sense here. If I were to graph y equals, let's say, 2 to the x, and I compared that to the graph of y equals 5 to the x. Okay, 2 to the x would look like this. 2 to the x would slide along the x-axis until you got close to slide along the x-axis until you got close to the y-axis, and it would go through 1 and then it would shoot up relatively quickly here. But y to the 5x, because the base is larger, what it's going to do here is when it's approaching the x-axis to the left here, it does it much closer to the x-axis. So it's going to ride along down here. Then when we get close to the y-axis, it's going to jump up. It's going to go through 1, and then it's going to increase much more quickly. Much more quickly. Now, when you do okay, let's convert these bases now to fractions here. When you've got y equals 1/2 to the x and y equals 1/5 to the x, now what's going to happen is this. Now we're going to have these decay functions here, right? But think of it like this. 2 to the x, it grew, it grew quickly, but it grew slower than 5 to the x. So this thing was going to, if I graph 1/2 to the x, it's going to look something like this. It's going to come down from high, and then it's going to go through y equals 1, then it's going to get closer to the x-axis. But 1/5 is going to drop down, and it's going to do it quicker. It's this kind of opposite effect here. Up here, the larger the base, the quicker it's going to shoot up. Down here, the smaller the base, the quicker it's going to drop down. Okay? So, take a look now at these two right here, 1/4 and 2/3. Which of those two is smaller? 1/4. 1/4 is 0.25. 2/3 is like 0.6 repeating. So this one is going to drop down much quicker. So now let's take a look at the graphs here. Here's C right underneath it, and here was A. Now we got to look at the scale here. You really got to consider the scale. Okay, and the scale is not too far off each of these. C looks like it's dropping down much faster. That has to be the value, the graph that corresponds to y equals 1/4 of x, or 1/4 to the x. So over here, because this one drops down a little slower, this one has to correspond to the larger base, y equals 2/3 to the power of x.
Classify each function as exponential growth function or an exponential decay function and state the y-intercept.
Okay, so this is just a matter of responding to the equation as we see it here. So notice the base of the exponential part of this is 4. That's greater than 1. So this is going to be growth. And then if I let x go to 0, remember order of operations, I have to do the exponent first here before I multiply that power by 5. So 4 to the 0 is 1, times 5 is going to be 5. So the y-intercept here will be 5. For this one right here, okay, again, focus on the power first. I know that there's a fraction in there, but focus on the power. The power is 2 to the x. The base of the power is 2. That's greater than 1, so this is going to be growth. Again, remember order of operations. When I plug 0 in, okay, if I'm going to evaluate for the y-intercept, you don't multiply 1/2 by 2 and then to the power of x. You're doing it wrong. We do the exponent before we do the multiplication, so 2 to the 0 is 1 times 1/2. The y-intercept here is going to be just 1/2. Okay, 6 to the x, take a look at the power here. Now notice that the coefficient of the power, it's not there. Like 6 is not the coefficient of the power. 6 is not a, it's the base of the power. And because the base of the power is greater than 1, this is going to be growth. Now, once you plug 0 into this, 6 to the 0 is 1. Well, that's it. There's nothing else to it. The y-intercept here must therefore be 1. Now, consider the power here. The base of the power is 1/4. The 2 is being multiplied outside the power. So 1/4 to the x. Because the base is between 0 and 1, this is going to be decay. Okay, now because the a value here is 2, okay, the coefficient up front is 2, that's going to be my y-intercept. I mean, you should start to be seeing the pattern here, but again, if you want to think about it like this, plug 0 in for x, and then you apply order of operations. Do the exponent first, 1/4 to the 0 is 1, and then multiply by 2, and then there's my y-intercept. But if you're really starting to see the pattern, well, my gosh, the y-intercept is always that number multiplied out front, then yes, that's the pattern. Use that. So here, I've got 0.4 to the x. That is the power, the coefficient here in front. If it's not written, I assume it's going to be 1. The base of that power is a decimal between 0 and 1, so this is going to be decay. My y-intercept here is going to be the same as the leading the coefficient of this power here, which is just 1. The y-intercept is 1. Here, I've got 1/7 as the coefficient out front. The power is 3 to the x because the base of the power is larger than 1. This is going to be growth. And then the coefficient here is 1/7, which means my y-intercept here is going to be the fraction 1/7. There you go.
Choose the graph below that best represents y equals ab to the x, where a is greater than 0 and b is between 0 and 1.
Okay, so let's just review what the question was telling us about the function here. First of all, where a is greater than 0. Now this means, got to interpret this, this means a positive y-intercept, because that's what a is going to be. Okay, it's going to be a positive y-intercept. A is greater than 0. And if I've got b between 0 and 1, this is going to be a decay function. It's going to be decreasing. So it should be dropping to the left here. So now, first of all, let's deal with this. Okay, the a is greater than 0. My y-intercept is going to be positive. Well, okay, it can't be that. because I can see right here my y-intercept is going to be negative. Oh, could be this one. My y-intercept is positive. Could be this one. My y-intercept is positive. Okay, can't be this one. My y-intercept is negative. Okay. Now, consider the fact that this has to be a decay function. So B and C were the only two that actually had positive y-intercepts here, so it's got to be one of these two. Which one of these things is decay? Well, it's this one. It's the one that decreases as you go to the right, so it can't be this one. Answer's got to be B.
Complete the following table.
Okay, so this is a good way of kind of re-emphasizing everything that we've just looked at here and putting it all on the table here. So we're going to look at y equals 2 times 5 to the x here. Now I'm going to run through the different pieces here before I sketch it. First of all, the x-intercept. I know that this sort of a graph won't touch the x-axis. There's no x-intercept. The value of A is the coefficient up front, is going to be 2. I know that the significance of the value of A is that it is the y-intercept. Okay. The domain, I know that this is going to be all reals. Okay. So x is an element of the set of real numbers. It's any number in the real numbers. The range, I know from before, whether this is growth or decay, that this is going to be y is greater than 0. Not or equal to, just greater than 0. The value of b is the base of the power. 2 is not part of that base, it's just 5. So the base here is going to be, the b value here is 5. Because this is greater than 1, this is increasing. So now I can go back up to my little graph here. I know that the y-intercept is going to be 2. It's supposed to be increasing. It's going to look something like that. Okay, let's take a look at this next one. Again, I'll sketch it in a second here. The first line here was supposed to be the x-intercept. I know that there's no x-intercept. Okay, I know that these exponential functions won't cross, unless you move these things. They just on their own, that kind of a function won't cross the x-axis. The value of A, the coefficient here, is going to be 3. So A is 3, and I know that that means the y-intercept is 3. That's what these two are here, the value of A and the y-intercept. The domain, again, there's nothing weird going on with that. It's just going to be an average. X is an element of the reals. The range here, so the domain is the element of the reals. The range is going to be greater than 0. It's not going to hit the it's not going to hit the x-axis. The value of b, let's go back up here. B is the base of the exponential. Okay, part of that, the power. The base is 2. This is going to be 2. Because that's greater than 1, this is going to be increasing. So now I can go up to my graph here. I know that it's going to have a y-intercept of 3. I know that it's increasing, so it's got to look something like that. Okay, there we go. The next one. 1/2 to the x. Well, what's the coefficient in front of the power? No, not 1/2, that's the base of the power, the number in front of the power. Well, if it's not written, we assume it's 1, which means that first line there, I'm already jumping ahead here. The first line is the x-intercept, there's no x-intercept. The second line here was the coefficient, which is just 1, which means the y-intercept is just going to be 1. The domain, once again, is going to be all reals. That doesn't change. The range is going to be greater than 0. That hasn't changed. What's the base? The base is 1/2. Because that is a value between 0 and 1, this is going to be decreasing. So now I've got everything I need. I know it's decreasing. I know it goes through 1. So here's 1 decreasing. It's got to look something like that. Has to. Look at the next one here. 4 times 1/3 to the x here. Now, again, this has no x-intercept. The value of A, though, the coefficient of the power, is going to be 4, which means the y-intercept is going to be 4. The domain, as it has been with everything else, has been all reals. The range, similarly, is going to be greater than 0. The base of the power does not include the 4, it's just the 1/3 to the power of x there, so it's going to be 1/3. Because it's a fraction between 0 and 1, that means our function is going to be decreasing. And now I can sketch this. It's a decreasing function that has a y-intercept of 4. So I come up to here, 1, 2, 3, 4, and that's going to be, it's quite high there. That's going to drop down. You know what? I want to make that look a little bit better here. I'm going to do it like this. I'm going to drop this down, and then I'll go 1, 2, 3, 4. There I go. So that's essentially what that's going to look like.
The growth of a plant during a 6-month period is modeled by the exponential function f of x equals 3 times 1.5 to the x, where f of x represents the height in centimeters, and at the end of each month, and x represents the time in months. Part A asks, use the graph to determine the height of your plant to the nearest centimeter at the end of the 4th month. Part B asks, what was the initial height of the plant, and what does it represent? And Part C asks, during which month was the plant double its original height?
So in this question here, the first one tells us to use our graph to determine the height of the plant to the nearest centimeter at the end of the 4th month. So what we want to do here is take this function and plug it into our calculator here. So 3 times 1.25 to the x. So 3, and we'll go 1.25. And I'm separating that with parentheses there because I want, the calculator will understand me if I then take this to the power of x here. Press enter. The calculator will understand that that multiplication by that 3 is going to happen after that. Okay, so it will get the order of operations correctly here. Now I'm just going to press, I'll press zoom number 6, zoom standard. Here's just my regular zoom settings. Now I need to understand that part of this graph really doesn't make much sense in this problem. Having this negative material back here is really not relevant. But I also know that a lot of people, this is immediately what they'll do, and then they'll just understand that this doesn't make any sense here. Okay, and they'll work with the material over on this side. The question is asking, how high is the plant at the end of the 4th month? So we know the very specific x coordinate. We're looking for the y coordinate. Now this is how you do this in the calculator. Okay, press second trace to get into the calc menu, and when you know the x value, you're going to use the first operation here, value. So you press enter. We're choosing value. Now the calculator is sitting here waiting for you to enter in the specific x value. So enter 4. This is the 4th month, and it tells us right here. Looks like we're looking at 7.3 centimeters. Okay, now it says to the nearest centimeter. We had 7.3 approximately, which is then approximately equal to just 7 centimeters. Whoops, sorry, you can't hardly see that. 7.3 centimeters or 7 centimeters. Now the next question says, what was the initial height of the plant? Okay, and what does it represent? Well, the initial height of the plant, that occurs, let's go back to our graph here. The initial height is when time is equal to 0. Now remember what we entered in here. The x coordinate represents time that has passed. So we're looking at the x-intercept of that graph. Now, I really shouldn't have to use the calculator to figure that out. Okay, this is the function that I entered here. I already know, based on previous problems here, that it's the value of that a that's going to be equal to my y-intercept. So I know that's going to be 3. But let's review how you would do this. Second trace to get in the calc menu. Not 0. At the y-intercept, you know what the value of x is. The 0 function here is looking for x-intercepts. We're looking for the y-intercept. So again, x equals, and I know that the y-intercept, the x is equal to 0. And there's my value, 3 here. Okay, so what was the initial height of the plant? We know that it was 3 centimeters. Okay, this is the y-intercept of the graph. Oops, y-intercept of the graph. And now finally here, during which month was the plant double its original height here? Well, you kind of needed to know that original one here to have that, to figure this out here. So we're looking at where this was 6 centimeters. And we're going to look for what time that occurs. Now this is a different problem, okay? A very different problem than the one that we had started with. Okay, over here, we knew how much time had passed, and it was very easy to just use the calculator to figure out what the y value is. Here, this is a y value, and I'm looking to figure out how much time has passed. When I go to my calculator, to enter in y values, I need to go to y equals. So then I go down to y2, and I'm going to plug in 6. This is the best I can do here. Okay, so there's my y equals 6. Here's the graph that represents the growth of the plant. This is where they meet. So I'm looking for where those two intersect. To find that, I'll press second, trace, once again, to get into the menu that allows me to do work on graphs here. And I'm looking for where those two graphs intersect. So number 5. Now the calculator, the questions it asks you now are fairly straightforward. What we're going to do first of all is move our cursor relatively close to that point of intersection. Now I'm not going to go right on top of it because I want you to see what the calculator does. The calculator is asking, is this the first curve? Well, yeah, it is. So press enter. And what it does is it jumps to the next curve that it has in its memory here. Then it's asking, is this the second curve? Now the reason why it's asking for that is because you could have 10 different graphs plotted. It just needs you to identify the two that you're looking for the intersection point on. Press enter. It's asking for a guess here. This is just to help speed up its calculations here. Just press enter to get past that. And it takes you to this right here. And so what we're seeing here is that after 3.1 months, we get to a height of 6 centimeters. So this is 3.1 months later. Now, let's think about that though, because you got to be kind of clever about this. 3.1 months means which month are you in? Well, let's think about the way the calendar works here. So here's the beginning of the year. Okay, here's the first month. This is January right here. Now, it's odd the way this works here, but even if you're like 0.1 of the way into January, 0.5 of the way into January, 0.75 of the way into January, okay, this is all in the first month. Once the first month is over, we're in February, and let's say in terms of the number of months that have gone by, let's say this decimal here, this is like 1.3. 1.3 in terms of time, if we're measuring months here, 1.3 means I've finished 1 month, I'm 0.3 of the way through the second month, but you're still in February. Okay, you're in the second month here. So when we have, when our time measurement is 3.1 months, this means 3 months have been completed and I'm 0.1 of the way into the next one. Therefore, we are in month, whoops, not moth. Oh, it's embarrassing when I spell wrong. Month 4. That's the answer. Okay, the plant will be double its original height in month 4 of this experiment.